All right, welcome back. Today we're going to be talking about derivatives. This is pretty much AP Calculus A. You learned way back in Algebra 1 how to calculate the slope of the line. How many points do you need for slope? Two. All right, and the basic idea is rise over run, delta y over delta x, however you want to compute it. But you need 2 points. If you have a straight line, what's true about the slope of that line? It's constant. Nice. So, fine. Straight lines are easy. But what if you have a curved line? How do you calculate a slope? Finding the derivative. Yes! Give me an algebra answer.
You must approximate the tangent.
Yeah, you got if you got a curved line like here, you've got to approximate the slope by, well, what you do, say if you wanted to, well, we can kind of do it by eyeball, and if we just take point 1 there versus point 2, which is steeper? Point 2 is steeper. How do you know that? Yeah, because your calibrated eyeball looks at it and says, oh, that looks steeper. Right? Or if you want to do it with numbers, you could draw a tangent line, this little red line right there, and then figure out what the slope of that tangent line is by, throwing it down on a sheet of graph paper, picking 2 points, and calculating a slope just like normal. And if you did that, you'd see the slope here is less than the slope at point 3. Oops, didn't mean to draw on there. Let's see if I can undo. I just hit it. It didn't do anything. Oh well.
Oh, there you go.
Alright. Alright, so that's how you figure out the slope of a curve. So, let's see. It turns out if the equation of this particular graph that we have right here is y equals x squared plus 1, the slope at each of those points, 1, 2, x equals 1, x equals 2, and x equals 3, comes out to be 2, 4, and 6, which is nice. But how do you figure that out? Well, links to physics. You guys all had physics last year. You know position versus time graphs and velocity versus time graphs. If the position versus time graph does something like this and makes a big curve, the velocity versus time graph has to be what?
Straight line.
Well, if it's curvy-uppy, it has to be increasing. Yes. Because the velocity is the rate at which position is changing. Okay. So there's got to be some way to figure out velocity from position. And, well, you could plot it out and do a whole bunch of slope calculations, or you could do something really simple, and it's called a derivative. All right, so doing a whole bunch of tangent lines, okay, that's a big pain in the neck. But we know if we want to find the slope of a curve, we just have to draw a tangent line and do the slope of that tangent line. Okay. Moving on. You guys all know this stuff. There is a quick way, if you have a function, any function, to figure out what the slope is at any point along that function, and that's the power rule. This works for any polynomial. The basic idea is, if your original function is x squared plus 1, all you have to do is 1 multiply each term by its associated exponent. So x squared gets multiplied by 2, so it's 2, and then decrease the exponent by 1. So x squared, the 2 comes down front, and you decrease 2 minus 1 is 1, so the answer would be 2x to the 1. Well, what if you have a constant plus 1? Constants just go away. So x squared plus 1 becomes 2x. X squared plus 2 becomes 2x. X squared plus 72 becomes 2x. All right, cool. That's called the power rule. All right, so a bunch of examples here, and you can read through them at your leisure. Now, distributive property, which I kind of skipped over, but here it is. It turns out if you have a polynomial function, 2x squared plus 3x plus 8, you can do the derivative of the 2x squared, the derivative of the 3x, and the derivative of the 8 all separately. The answer for this comes out to be 4x minus 3. Sorry, plus 3, right. Thank you. Next one. Mentioned before class that e to the x is special. The derivative of e to the x is e to the x. So how do you do e to the 2x? Well, same rule as before, except whatever is in the exponent stays the same. So e to the x is e to the x. E to the 2x, the 2 comes down front, but the 2x in the exponent stays the same, so 2e to the x, etc. And you can read through that list. Lastly, trig functions. Trig functions are weird. Are you guys aware that all the trig functions can be expressed in terms of e and I? You know that?
Oh, that weird equation.
That weird equation? What am I referring to?
Thanks. That with the pi and the...
Yes. E's and pi's and i's. That sound familiar? Yes. Yeah. I actually, I don't know if I want to go here yet, but whatever. Well, let's do it. When I was in multivariable calculus in college, I had a professor, and I don't know how religious you guys are, but he made the claim that he had proof that God exists. And the proof went something like this. So he started writing things on the board, and what he wrote was this. E what's E?
2.71.
It's the natural number, right? E is the natural number, whatever that means. It's some number. But when did you first encounter E? Do you remember in your mathematical travels?
We're doing logs.
But when did you first use it, though?
Like what math?
Like what practical interest, right? That was the number that you used when you were doing compound interest, and you were compounding continually. Remember that? And that's like the real life practical example that you learned. So E is the number that has to do with compound interest. Okay, good. And then, okay, so the next number he wrote on the board was this. Pi. Now, when did you first learn about pi? Circles, right? What's pi?
3.141.
No. I want to know what it means.
It's the ratio.
The ratio.
The circumference to the diameter.
Circumference and diameter. Something like that, right? Yes. That's exactly right. Circumference and diameter. So E is the number that has to do with compound interest. Pi is the number that has to do with circles. And then the next number he wrote on the board is I. And what's I? It's the square root of that. It's the number that doesn't exist, right? It's the square root. It's completely imaginary. It's make-believe. So now we've got the compound interest number, the circle number, the imaginary number, and then the last thing he wrote on the board was an equal sign, -1. True or false? E to the pi I equals -1. Pull out your calculators.
does equal negative 1.
It does equal negative 1.
Why?
But why? Isn't that freaking bizarro?
It is freaking bizarro.
E to the pi I equals negative 1.
Where's the
It's on the bottom.
How the heck can that be?
It doesn't exist. There's something like that.
Oh my gosh.
Pi I. No, that wouldn't even work.
Oh wait, something.
So the compound interest number raised to the power of the circle number times the imaginary number is negative 1.
Okay.
Exactly. Now, I'm not going to go into why that is at all, but it has some pretty amazing implications for all sorts of things, one of which is trigonometry. And you can use this relationship, or this relationship is used in talking about why the derivatives of trig functions do goofy things and repeat each other. And it also has to do with Taylor series, which I'm not going to go into at all. But you guys will become very familiar with. Got it? So anyway, that was my professor's "Why God Exists" speech. But I thought it was pretty cool.
They didn't explain, like, can you work it out?
No,
No,
it's just
do you want to?
bizarre, but true. But true.
Can you give us a proof?
No,
Oh.
no, not beyond the scope of this course. But you can look it up.
And this course is already like.
Yeah. All right, so I am going to state without proving that explains the next thing I'm going to explain, which is derivatives of trig functions. And why the derivative of sine is cosine, and the derivative of cosine is negative sine, and the derivative of negative sine is negative cosine, and the derivative of negative cosine is sine, which you guys all, I think, did in AP Physics B. But you certainly did it in calculus and calc A. So, anyway. All right, kinematics examples of derivatives. Let's see. Why don't we do these? Nope. Yeah, let's do this. The position of an object falling from the top of a 100-meter tall cliff is given by the function y is a function of time equals 1/2 AYT squared plus your initial y position. Find an expression for the velocity and accelerations as a function of time, given that the acceleration due to gravity is 9.8 meters per second squared. Go. Okay, here we go. Velocity is derivative of position. What happens to the 100 term?
Goes away.
Goes away. So we're left with velocity equals negative 9.8 times time. Okay. Does that equation look familiar at all from last year? Maybe, maybe not, right? That just looks like the answer to a problem I gave you, right? Okay, whatever. We'll move on. Oh, so the acceleration is, well, negative 9.8. Hey, negative 9.8 meters per second squared.
I don't know what that is.
Wow!
Cool.
Look at that! Calculus. I think I'm going to get back to that velocity equation in a second.
Therefore, cool.
Therefore, cool, huh? Absolutely. All right.
Good catch.
And as you guys already know, this is called, the acceleration would be the second derivative of position. In physics, what do we call the third derivative?
Jerk.
No.
No.
We don't call it anything.
Oh.
That's a made up math word. No, we don't have a specific word for that idea. The idea exists, is you just have a word that. Well, what would that imply? That would imply the force is changing, right?
Right.
So what's the word that you use to describe a force that's changing? A changing force, right? That's it. So, yeah, we don't really have a special word for it. The change of the rate of change.
There actually was another
What
one.
about a delta force?
Delta force, you can have that. That's right. You can. It is a movie. Yes, it's an organization.
But it actually makes sense.
Yes. All right. All right. Next one. Simple harmonic motion example. This one's a little more fun. Position of a spring mass system. We're going to be doing a lot of these ones, by the way. Given by the function, position as a function of time equals a cosine 2 pi over period times t. What's that a mean physically?
That's the amplitude.
That's amplitude. What's that?
How far it moves from its initial position.
How
and
far it
either
moved
left or right.
from initial position? What if it starts over here?
The equilibrium.
Yes,
That's it.
amplitude is how far you move from equilibrium position. Nicely done. All right, what's this capital T? Why is there a capital T and a lowercase t? Capital and lowercase.
T is the period. And T is
Yeah, capital T is period. What's period again?
the time it takes to make one.
One complete oscillation. Nicely done. And what's lowercase t?
That's time.
That's just time. That's the now time on your watch, right? Okay, so. All right, so if that's the position as the function of time, what's acceleration as a function of time? Go. Acceleration is a function of time. There's velocity. Velocity was a negative sign, right? Everybody get all the constant stuff in front, right? 2 pi a over period. And you go one more and you get acceleration. And you get, with acceleration, look at all that. Negative 4 pi squared over t squared times a. Times cosine of this stuff in the middle. Does that look familiar at all? 4 pi squared over t squared?
The frequency to period function.
Where have you seen that before? In what context did you see that? Yeah, something to do with rotation, circular motion. Remember uniform circular motion? And we said we had something like the centripetal acceleration is 4 pi squared r over t squared. Guess where that comes from? Got it?
Oh, wait.
All right. And I believe that's it. Nicely done.